Good afternoon. Good afternoon, boys and girls. Thank you. Thank you all for joining us today. We really enjoy seeing a great crowd like this, but not at all surprised given who our speaker is. We've had a very busy summer here at the Milken Institute, and we're looking forward to an even busier fall. We have a lot of events going on. We're going to be, we have our third annual London Summit, which will be going on in London, oddly enough, at the beginning of October. We're going to be doing a very nice event in Washington at the beginning of September, which is going to be introducing the new head of our Center for Financial Markets in our DC office to members of the Senate and the House and the administration. We have a nice reception for them. We have our wonderful Partnering for Cures event, which takes place in New York at the beginning of November. It's an incredible health conference, but also a great investor conference that puts together people who are trying to find cures for diseases with people who might fund that. We are going to be introducing the new managing director and chair of the Milken Institute Asia Center in Singapore, and we'll be putting out an announcement on that very shortly. We have some major research that we'll be releasing, and on and on. We have a lot going on. In terms of forums, we have an upcoming forum on food and America's well-being. It's going to be moderated by CNBC's Jane Wells. We're going to have an all-star panel that includes Lori David, Michelle Baker, the director of Google's Food Services, and Robert Eager, the founder of LA Kitchen. That's going to be here on September 10th. That's for those of you who aren't in Washington, September 10th at the event we have there, but for those who are here. On October 25th, we're going to have a forum featuring a couple of illustrious brothers, Tom and David Kelly of the legendary Silicon Valley design firm IDEO. They're going to be here to talk about their forthcoming book, Creative Confidence, Unleashing the Creative Potential Within All of Us. Actually, it's within us all, but that's very close. And that should be a great forum. We hope you'll enjoy that. And we have some more on the calendar we'll be announcing then. And, of course, details on all of our events can be found on our website, milkeninstitute.org. Now, there will be time for questions after Dr. Elachi's remarks, but we're going to, as we have at recent forums, going to be taking these primarily electronically. We found that allows us to get through far more questions. So here's how you do that. You get ready to text or email questions during the talk. So you do it to the addresses that are, I think it'll be shown here. Yes, they are. Good. That's forum questions at milkeninstitute.org if you're emailing, and texting 310-751-0715. For those of you who do not have an electronic device, get out a pen and paper, write something down, and convince the person next to you to text it or email it for you. Now, it really is a pleasure and an honor to introduce today's speaker. Charles Elachi is director of the Jet Propulsion Laboratory in Pasadena. For more than 4 decades at JPL, he started while still in kindergarten. He's been a leader in developing the field of spaceborne imaging radar. He's been the principal investigator on many studies and flight projects sponsored by NASA. He's currently the team leader on the Cassini-Titan radar experiment and a co-investigator on the Rosetta Comet Nucleus Sounders experiment. Elachi is the author of over 230 publications, the holder of several patents, and the recipient of honors too numerous to mention. But there's one that I really do have to mention because it's an honor we all wish we could have. In 1989, an asteroid was named 4116 Elachi in recognition of his contributions to planetary exploration. How many of us would like to have our names zooming around the universe? It's wonderful, although there are people we know who we'd like to. That's right. All right. A year ago, Dr. Elachi and his colleagues really did thrill the world as we watched Curiosity, after a 350 million mile trek from Earth to Mars, make a perfect landing within its target 2-mile wide area. Now, to put that in perspective, that feat is comparable to hitting a golf ball in Boston, having it land on a specific seat in the Rose Bowl. As one commentator marveled, for the Twitter generation, this was our moon landing. And to thrill us further, Twitter or no Twitter, Dr. Charles Elachi. Thank you.
Thank you very much. Thank you very much, and it's a pleasure for me to be here. Particularly, I'm excited when I see a number of the young people who are here. Not that I have anything against senior, like me, but they are the future of our country, so I'm always excited to see them here. As was mentioned earlier, a year ago last week, we landed the car-sized rover on Mars. This probably was one of the most challenging technological accomplishments that we have done in space exploration. And not only it was very challenging, also it was a very tense event, and it was probably one of the most innovative way of how you actually go and land on another planet. So even that's going to be the main topic of what I'm going to discuss today, but I thought that before I do that, I will try to explain to you why we do exploration. Why is our country, spend money to actually explore space? What's the benefit of it? And then also, and put that, in that case, put the Mars mission in context of why we're doing it. And then at the end, I'll also will describe a couple of examples of things here down to Earth that we are benefiting from the space program and from the technological achievement that we have been doing. So let me start first by explaining to you why we are doing, exploration. So somehow, about 13.8 billion years ago, there was a Big Bang. Now, don't ask me what was before the Big Bang and how did it happen. I have no idea. But anyway, there was a Big Bang, and a number of particles were created at that event, and somehow those particles got together and they formed stars and galaxies, like what you see in here. This is an example of 5 galaxies, a picture. This is a very teeny part of the sky, and there are literally billions and billions of galaxies in our universe, and these are only 5 of those few billion galaxies. And if you look and zoom on one of these galaxies, each one of these galaxies literally has billions and billions of stars in it. And our star, the sun, is just one little teeny dot, in a similar galaxy to what you see in here. And then somehow it turned out around some of these stars, which turned out to be the vast majority of them, there was a disk of dust and particles, and the particles kind of got together, agglomerated together, and they formed the planets. Example is our solar system. That's what our solar system is. These are to scale. So our planet is that little teeny blue dot, the third from the right. And then somehow on that one of those planets, which is our Earth, we had the right environment, the right temperature, the right everything, which led to have organic material and cells, which led to the beautiful world that we live in. And then after 3.8 billion years of evolution, because our planet started about 3.8 billion years ago, then you got the Milken Institute. Now, not many of you realize that it took 3.8 billion years to have the Institute, in here. But the point I'm trying to make, isn't that amazing? How did it start from these particles 13 billion years ago? And here we have people like you and I sitting down having this conversation here. How did that happen? What led to this? How did star happens? How did planets occur? How did life evolve? And then how common is it? Is it only on this little dot, which will be kind of amazing if it's only at that one point, considering there are billions of stars and billions of galaxies. And if it's common, that would change completely our thinking about our place in the universe. And if it's rare, if it's only on this planet, that's equally amazing. Why did it happen on this location? So what we are trying to do in our space exploration is to what I call write the book of how we got here. Basically writing the book of how did the star form, how did galaxies form, how did planets form, how common planets are in the universe. Do they all have life on them? Do they have the right temperature and the right chemistry? Do they have the right ingredient on them? So basically it's writing the story of how we came about. So that's basically what we're trying to do. Now, this doesn't happen overnight, and it doesn't happen by doing one mission. It's really a quest that probably will take us decades to do that. And today I'm going to just describe to you just one chapter of that book, is by telling you what we are doing, particularly in the case of exploration of Mars. So now let me tell you about Mars a little bit. Why are we focusing on it? So I just put here a picture. These are roughly two sizes, Earth and Mars next to it. Mars is about 1/4 the size of Earth. But as you know, the ocean is 3/4 of the surface area. So if I take the oceans away, Mars and Earth are about the same, size-wise. So Mars is a big place that you can explore. Mars has a lot of similarity with Earth. It's the nearest planet to us with Venus, so depending on the orbital mechanics, one of them is nearer than the others. Mars has polar caps, similar to what we have on Earth. There is ice in the North Pole and ice in the South Pole. It's water ice, and they expand and shrink depending on the season. Mars has similar season. The year on Mars is the equivalent of 2 years on Earth. So that's how long it takes Mars to get around the sun. The day on Mars is 24 hours and 20 minutes. That's how long it takes for Mars to rotate around its axis. So you have morning, evening, you have spring, winter, fall, exactly the same say we have on our planet. Mars has atmosphere, much thinner than ours. It's about 1% the thickness of our atmosphere. That's the equivalent of when you are flying at 10,000 feet. So that when you are flying in a jet, that's about the density on Mars. It's mostly carbon dioxide. During the day on Mars, during the summer, at noon, at the equator, the temperature is like outside today, here. However, at night and in the winter, it goes to like minus 150 degrees. So it's very, very cold at night. So there is a much larger extreme of temperature that occurs on Mars. So let me give you a more focused picture. This is two pictures here. One is of the Grand Canyon on Earth, and the other one is the Grand Canyon on Mars. So Mars is the one on your right, and the one on the left is the Grand Canyon on Earth. They look very similar. I could have told you the picture on the right is from Earth. You would have believed me. This is a more closer picture. The one on the left is from the surface taken of the Grand Canyon. The one on the right is a picture taken from one of our Rover, not the one we have now there, but the one we launched many years ago. And you see the similarity. You see this layering in the rocks. Now, for a geologist, they love layers in the rocks. And the reason they love that is because the layer tells you the history of what happened in that location. Because the top layer is the most recent. The layer below it is a little bit older. The layer below it is a little bit older. So by analyzing these different layers, you are going back in history of what happened in that location. By analyzing the composition, by analyzing the chemistry, so by looking at these different, or if you see fossils, so that's how we know certain fossils, what's the age of them, is by looking at what layer they actually were embedded in that area. And you see very similar between the two places. There are volcanoes on Earth, there are volcanoes on Mars. The picture on the left is a volcano in Northern California. The picture on the right is a volcano on Mars. Matter of fact, it's the largest volcano in the solar system. That mountain that you see there is about twice the height of Mount Everest. So when it formed, now it's dead. I mean, there is no activity going on now. But when it formed, clearly there was a lot of volcanic activity to create that volcano. It's many times the size of the island of Hawaii. So clearly there was a lot of volcanic activity on Mars at some time in the past. This is a test I give to my student at Caltech. I guess which one is Death Valley and which one is Mars. They look very similar. Sometimes I even forget myself because I forgot to put the label on them. I think the one on the right is Mars and the one on the left, is Death Valley. But the point I'm trying to make here is that the geologic activity are very similar. So if in the future an astronaut lands on Mars, she will think she is in Death Valley. So it will look like a very familiar place for us. It's not like the East Coast and rain and forests and so on, but it's a very familiar place that will be for us. So the key question that we have is, okay, if it's so similar to our planet, and as I will show you a little bit later, is that we found out that actually there were oceans on Mars a few billion years ago. They don't exist now, but there was on Mars before. The question is, number one, what happened to those oceans? And number two, could have life started? I mean, we believe that life on Earth started a few billion years ago in the oceans. Mars has the same chemistry, the same geology, the same everything, and there were oceans in the past. but somehow they disappeared and the volcanoes kind of, are extinct now, could have life started? And if it did, what kind of life did it start? Did it have the same DNA that we have in here? Did it have the same chemistry, or are they different? And how far did it evolve before things stopped? Evolve? Did it get to a cell level, or did it get even more than that, or less than that? So that's what we're trying to do in learning more about a similar environment. And in the long term, is it a place which is habitable? If our great-grandkids want to move and travel and explore another planet, is that a place which is amenable, for life? So let me now describe to you the challenge it is to get to Mars. If Lewis and Clark were heading toward Mars, it will take them 40,000 years to get there. If Columbus is sailing toward Mars, it will take him 10,000 years to get there. And that little green car, some of you my age remembers, that's a 260Z. I still drive that car. That's what I go to work, back and forth. It would take almost 175 years driving 24 hours at full speed, to get to Mars. So that gives you an idea, roughly how far Mars is from us here. Now, with our spacecraft, it takes us about 9 months, at the speed of the spacecraft that we will do. Let me give you another challenge, which was kind of mentioned a little bit earlier, but I'll give you a different twist on it. After Curiosity, after traveling 450 million kilometers, we had to land within 2 kilometers. To give you kind of a different illustration, that's the same as if you go outside and hit a ball toward a golf ball towards St. Andrews, and it has to land straight in the cup. That's how accurate we have to land. Now, to make it a little bit more challenging for the good golfers, that cup is moving at high speed also, because Mars is moving, and you still have to get straight in the cup. So that gives you an idea of the navigation challenge that we had to do to actually be able to get there. And we had to develop a lot of technology, which ended going into the GPS satellite and the GPS technology. It's a little bit different, because we don't have satellites around Mars, to guide us. But that's the kind of technology we had to develop to be able to be so accurate, in our landing. Let me give you another example of a challenge. When we were arriving at Mars, we were arriving at the speed of 18,000 kilometers per hour, or 12,000 miles per hour. So that means you can go from here to the East Coast in like 15 minutes. And if you take the amount of energy in the capsule that was coming in at that high speed, if you are technical people like the gentleman sitting here, that's 1/2 mass multiplied by velocity squared. The energy coming in is the equivalent of 18,000 race cars going at full speed. That's how much energy were coming in. And in 7 minutes, which is the time it takes us from the top of the atmosphere to the surface, we had to dissipate that energy and land softly on the surface. So that's another one of these little challenges that we were facing. So now then came the trick of how do you land, on another planet. Now, one thing I haven't mentioned is the signal from Mars to Earth take about like 10 minutes, to 15 minutes, 14 minutes, depending on the time. So you cannot joystick. You cannot sit down and joystick your landing. Everything has to be done autonomously. And as I said earlier, you have to dissipate all that energy as you are coming in. So the first thing we do, we have a heat shield, so we slam in the atmosphere, and we use the drag in the atmosphere to slow us down. But the atmosphere is not thick enough to slow us enough. So the next step we do, as I'll show you in a video, then we open a parachute at supersonic speed, and it's the largest parachute ever built. So that slows us down, somewhat more. Now, on Earth, because we have a thick atmosphere, you can come on the parachute all the way down, like a parachutist does. But on Mars, its atmosphere is too thin, so it doesn't slow us enough. So we have to come with additional tricks. So after we do that, then we fire a retro rocket to slow us even further. But then the problem, if we take the retro rocket all the way down to the surface, it's going to create all kinds of dust, and rocks are flying all over the place. It could damage. So we need another trick, after to be able to land softly. So when we landed Spirit and Opportunity about 7, 8 years ago, or 10 years ago now, then just before we touched the surface, we inflated the airbags, all around the lander, like your car airbags, and that allowed us to bounce on the surface, and when we stopped, we deflated them, and we came out from the airbag. On Curiosity, the one we did a year ago, the rover was just too big. It was like 10 times bigger than Spirit and Opportunity, so airbags would not work. So the trick we came up with is to come and hover above the surface, at about 30 feet, and then just sky crane the rover from the lander down to the surface. So just imagine you are sitting on another planet and we're hovering and descending, all that, and everything has to be done completely autonomously. So that means we have to test it, we have to develop it ahead of time, and so on. So now what I'm going to do, I'm going to show you a video, which first you'll see some of the testing, we did. So you see how do we prepare for these things. And then there will be a few segments where actually some of the engineers who worked on it to tell you about how nervous they were, and the challenge that we're facing. Then we'll take you in the mission operation room and across the country, so you see what actually was happening at the time when we landed in there. Now, to give you a heads up, part of the movie is animation. But it's not animation like Disney. It's animation which is driven by actually what was happening. So when you see something coming in or inflating or something, it was happening on Mars, but we didn't have a camera on Mars to watch it, so we did some animation. And in some situation, you will be seeing the picture taken from the rover as it was landing. So you will be seeing, and I'll try to point it out for you. So it's actually what we were watching as it was coming down, to the surface. And I would like you to notice a couple of things. One is the age of the people who were there. They were mostly in their 20s and their 30s. There were a few people like me, trying to act smart, in the back. But really the smart people were the younger people who were doing all that work. And see the nervousness, on their face as we were progressing, as we were going down to the landing. So let's see if that all works.
Six, 5, 4, 3, 2, 1. Main engine start, 0, and lift off.
So that's when we separated from the rocket and we were heading toward Mars.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
Things are looking good. Coming up on entry. Vehicle reports entry interface. At this time, it'll begin pressurizing the propulsion system to increase the thrust of the system. It'll use that for all the maneuvering in the atmosphere we're about to do. We are standing by for guided start of guided entry. We are beginning to feel the atmosphere as we go in here. The vehicle has just reported via tones that it has started guided entry. At this time, the vehicle is beginning to steer its way to the target. We have seen peak deceleration.
Yeah, we had 50 million
starting
people in the
first
United
angle.
States alone watching.
It is
real
reporting
time.
that we are seeing Gs on the order of 11 to 12 Earth Gs. Tank reversal 2 is starting. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Feat shield has separated.
So
We're
that's
down the
an
ground.
actual picture
We're down to
taken
90
from
meters
the
per
lander
second at an
coming
altitude of 6.5 kilometers and descending. Standing by for back shell separation. We are in powered flight. We're at an altitude of 1 kilometer and descending. Standing by for sky crane. Sky crane is started.
Signal to us, you remain strong.
Touchdown confirmed. We're safe on Mars. Time to see where our curiosity will take us.
Not very often you see engineers crying.
We got thumbnails.
Today, right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars. This is an amazing achievement.
Well, today on Mars, history was made on Earth. The successful landing of Curiosity marks what is really an unprecedented technological tour de force. It will stand as an American point of pride far into the future.
Well, tonight was a great drama that was played. I could only think of the words of Teddy Roosevelt as I was sitting there. It is far better to dare mighty things even though we might fail, than to stay in the twilight that knows neither victory nor defeat. Thanks. Now, I want to mention to you a couple of anecdotes on this thing. I mean, for me, clearly the landing was a very exciting time. But what was even more exciting is the emails I got the following day from people I didn't even know, or people saying how inspirational that was, how their kids, stayed up all night, to watch this thing, what our country can do when we put our mind to it. Matter of fact, there was a quote in Time magazine which said that despite all the dysfunction in Washington, the successful, well, we know that part, but the successful landing of Curiosity showed what our country still can do when we put our mind to it. And that's really something which is very uplifting, for me and for many of the people who worked, on this program. The other one, which was interesting, is that during the landing, we had the head of the French Space Agency, we invited him, and the deputy head of the Russian Space Agency. And after the landing, I saw them in the hallway, and they looked at me and they said, only the United States can do this. So that alone, make you feel really proud of the accomplishment that what the people have done in there. Now, as you saw, the people who were watching it, there were on our website, and we kind of estimated on people watching on TV, there were 50 million Americans watching the landing in real time. Now, when I'm in Washington, I say usually 50 million voters were watching. That usually, that gets people attention, back there. And the following day, in 24 hours, we had 1.6 billion hits on our website. Now, some of them were the same people, repeated. Like me, I was checking every 5 minutes to see what's happening. But it shows you kind of the excitement and the engagement of people, and doing the kind of thing, exploration our country is doing. So first thing after we landed, okay, we do the same thing that your kids do when you give them a little iPhone. The first thing you do, you take the iPhone, you take a picture of yourself, and you send it down. So that's what we did. So the rover had an arm on it, and at the end of the arm, there is a camera. So the arm, we extended the arm and looked to see, did we land safely, anything, which got them kind of examined ourselves, looked under the rover. Now, I'm sure the smart people here, you are all smart, will say, well, where is the arm? We don't see it. Well, we did some photoshopping on this thing. So we kind of erased the arm in there. On the original picture, you would see a long arm sticking, from it. So everything looked nice and safe. So let me describe to you the rover a little bit. As I said, it's about the size of your car. It has 6 wheels. It's all electrically powered. At the tail end, at the back, you see what looks like fins, white fins. It's a small nuclear reactor, and it generates 140 watts. It's about 2 bulbs in your home. That's all what we need to run this rover. Now, we have batteries which accumulate, the electricity and the energy to allow us to drive. But we run on just 140 watts for that rover. Then you see on the boom in the front, basically it has a series of cameras. So we have stereo imaging. It's like your eyes. So you can get 3-dimensional imaging that we get down to the ground. It has a laser system, which is a very powerful laser. So if we see a rock far away and we're interested to know what is it made of, we can zap the rock and basically ablate the surface of the rock. And the gas which is being emitted, we can analyze it remotely and determine what is the rock, made of. And if the rock is interesting, then we can get closer to it and actually drill through the rock, grab the samples, with the arm, and put them inside the rover where we have a series of chemical instruments. So we have X-ray instrument, exactly like what your doctor has, and so we can get X-ray of the crystals, so we can determine the composition. We put some of them in ovens and heat the material up to a few thousand degrees and see what gases are being emitted from it. And then we can do what we call mass spectroscopy, that we can determine exactly what are the chemical elements that the material is made of. And all of that is done autonomously in that little rover. So there was a lot of technology we developed to miniaturize things which are like the size of, a refrigerator, in a chemistry lab, and that will be able to compact it and put it in a small area. So, of course, there is a lot of humor in this business. So we got this email about somebody sending us a bill about parking in the wrong place at Gale Crater. But my favorite, sorry, let me go back. Yeah. Oops, sorry. I thought there was a slide there, but that's okay. But the other piece of humor you see in here, on the wheels of the rover, we always put a pattern on them, like we punch holes in it. And the reason we do it is that when the wheel turns a complete circle, we see the print on the surface, so we can tell how far it drove. So what we did, the guys were very ingenious at JPL, so the pattern in the holes is a Morse code for JPL. So as we rove, you have on the ground printed JPL, 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 on Mars. So now that's where we are now. So if you look carefully at this picture, at your left, this was taken from a satellite. At the left where you see the dark areas, that's where we actually landed. So this is the dust which was blown away from the retro rocket as we were coming on the landing. Then you see kind of a wiggly line, across the center of it. These are the tracks of the rover as we were driving. And I think on the next picture, you'll see where's that white dot. That's where the rover was about a few weeks ago. So we actually can see the rover on the surface, of Mars. And we drove to that area which is bound between the white area and the brown area because we thought that's interesting. So we wanted to see what is that area, made of. So what we found first, which got us pretty excited, was the pictures that you see on your left. We saw this kind of layer of rocks. And on the right, we have a similar example on Earth. Now you say, why is that exciting? Now it's, as you could imagine, geologists get excited about all kinds of funny things. So here, the reason this was exciting for us is on Earth, if you look at the bottom of a stream, all the rocks are rounded. Now rocks don't start rounded. They start to be very sharp-edged because they are broken. But then as they are tumbled inside the water river, then they get smoothed out and they become rounded. So when you see rocks which are rounded, that's an indication there was a river there or a fluid flow which tumbled, all those rocks. That's like you do in your tumbler, to polish rocks. It's the same thing which happen in nature. And then after a while, they get compacted and they form what's called conglomerate. So what you see on the left is very similar to what you see on Earth, which was from a bottom of a stream. So that was the first indication that we landed in a dry riverbed. So we continued driving, and then we saw some sand dunes, so we picked some samples. You see the arm of the rover. So we picked some samples and did some analysis. And then we went further. Oops. And this is the area we were particularly interested in with the rover because it looks like a wash. And then if you look carefully, it looks like mud cracks, on the surface. So that's an indication that maybe water was there, and then when it dried up, you get these cracks that you see at the bottom of a lake when it dries up. So, of course, we went and drilled the hole and took some samples for it to do the analysis. Now, again, as I tell you, geologists get excited about funny stuff. This was very exciting just looking at this picture. And the reason is, you all know that Mars is called the red planet. And the reason it's called the red planet because it looks red. The reason it looks red is because the surface is basically rusty. It's oxidized. And it's rust like you have on your metal. And that's done by oxygen. Well, oxygen is not very friendly for organic material. That's why you take out the oxidant, because organic material don't like too much oxygen. So a big concern was how deep is that layer of oxidation, or how thick is that rust? And could the life be close to the surface, or is it too deep, below the surface? So when we drilled, and as soon as we start seeing gray material, everybody cheered, because that indicated that the rusty layer is very, very, very thin rust. So that means you don't have to go too far down. You have to go fraction on an inch, and you can get to material which is not oxidized. To make a long story short, we got these samples, we examined them, we did the analysis, and basically the bottom line, everything in your body, every element in your body, oxygen, nitrogen, phosphorus, hydrogen, everything which is in your body actually exists on Mars. So the key question, next question is, did those elements get together and form organic material? So the basic ingredient that are on Earth, which led to life, which are in your body, in our DNA, actually exist on Mars in the same way that exist on Earth. So the next question, we haven't seen life, so I don't want people to go tweeting that we actually saw life on Mars, but basically all the ingredients for life actually exist on Mars. So the next step we're going to try to do is to see if we can find organic material. So we still have a couple of years of exploration that will be going, looking at different layers in the rocks and do analysis of those layers and see if we can find any organic material. I have no idea if we'll find them or not, but that's what exploration is all about. So now let me tell you a little bit of a personal interesting thing which talks about people innovation. 3 years before we landed or before we launched, I got a call from a reporter in Italy, and she's a science reporter. She sometimes covered all the missions at JPL. Said, well, we'd like to invite you to come to Turin to the Royal Library and look at Leonardo da Vinci Codex of Flight. So I kind of was wondering why am I being invited? So I asked him, why is that? He said, well, we really would like to see if there is a way we can scan that Codex of Flight. This is the original handwritten book by Leonardo explaining how birds actually fly. And that was led to a lot of the technology we do now on airplanes. She said, we would like to see if we can scan it and put it on a chip and put the chip on the rover so we can say Leonardo went to Mars. So I thought, well, I'll have to see if we can do that. But I was intrigued enough, so I went to Turin. I was visiting Italy with the space for Italian Space Agency. So they take me in the vault, where they have all the original one. And they put the gloves on my hand, and they let me actually go through the actual original document that Leonardo actually wrote. So for an engineer, my hand was trembling when I was, doing that. And that's what you see in here. But what really was intriguing for me is, look at the next picture. The one on the left is a drawing in that book. The one on the right is a picture of our lander. Now, he was not doing it for landing on Mars, but it was amazingly similar. Look at this one. The one on the left is a drawing in his book, and the one on the right is after we dropped the heat shield, to do that. So Leonardo was talking about if we build flying machines, in Earth. He was not thinking about Mars. How would you design them? He never built many of these things. But it shows amazing the imagination of human being and people like Leonardo and people similar to that. So needless to say, we agreed to actually scan the Codex, flight, and it is actually on Mars now. And as you can imagine, the Italians are very proud of it. If any of you are in Washington on September 12th, that Codex of Flight is going to be displayed in the Air and Space Museum. They brought it from Italy, and there will be a talk that I'll be participating in, on actually that we scanned it and we put it, on Mars. So that kind of finished my story about Mars. So the next question say, okay, what other things, we're doing? How are you benefiting in addition to the intellectual benefit and the knowledge about life? So let me give you a couple of examples. This is an example of some of the technology we developed in our space mission to actually be able to image earthquakes from space. This is the earthquake which happened in Japan, and those patterns, different colors, red and blue, that show how much motion occurred on the surface, fraction of inches of motion, which happened as a result of that earthquake. Now, you would say, well, what's the benefit after the earthquake happens? We would like to know it before the earthquake. Well, as we develop this technology, we believe we can actually map faults, like the San Andreas fault, and determine how much stress is occurring, how much bending of the rocks is occurring, down to fraction of an inch, and to be able to say this area is high risk and this area of low risk, because we see a lot of bending, which is happening in the rock on fraction of a millimeter or fraction of a centimeter. So that's one example of potential benefit. And this is technology which could become operational in the next 4 or 5 years. Another example is to look at actually what happened for the water table. As you know, water is probably one of the most important things to manage. So we have developed technology where actually we can measure from space how much water there is below the surface in the water table. Now you say, how in the heck do you do that? Basically what we do, we measure the mass of the water. So we measure the gravity field, and if you pump out about an inch of water, there is less mass. So we can measure the gravity change even from a satellite altitude. And what you see here is an example of monitoring the water table between India and Pakistan, how much pumping actually was occurring over the last few years. So as you could imagine, for people in the Central Valley, we'll be able to tell them on a weekly basis how much water there is in the water table, how much water is coming from the Sierras, coming into the water table, and as we are pumping water, how things are changing. So that's a day-to-day practical thing that people can benefit, from it. The other example that you will see in here, we are able to monitor the surface of the Earth, and if there is any bending or any change in the surface. Now you say, why is that important? So again, if you are pumping oil or you are pumping water, you are taking material from below the surface, so the surface will subside, a little bit. And when I talk to farmers in the Central Valleys, that's a big deal for them, the subsidence which is occurring on the surface. Matter of fact, this area, actually we were planning to put the high-speed train that are being talked about across that area, which would have been a bad thing, because after a few years, the surface is going to come down many tens of inches, and that's not the place you want to put, rail lines in that area. Now, this one is a picture which is not related, kind of related to us, which was taken about 3 weeks ago or 4 weeks ago. We have a spacecraft which is in orbit around Saturn. And it turned out that 3 weeks ago, the sun was just behind Saturn relative to the spacecraft. So we looked toward Earth, and we took a picture, of Earth. So you see on the top left that that's Saturn itself, but it's in the dark because the sun is in the back. You see the rings, and that little white dot, that's us. See how small we are. And if you look at the picture to the right, which is the blow up of it a little bit, that's us and the moon next to us. So that little dot is all of you, all your friends, all your enemies, all the people you like, or the people you don't like. All of them are living on that little dot, in space. So I think that put us kind of in a perspective, where we are in this solar system. And that's kind of a more detailed picture of it. If you go on the JPL website and you want to have your own picture. Matter of fact, I'll tell you also a little anecdote. I was at a club up in northern San Francisco, and there was a group of people there, and we were sitting down listening to outside, and we were listening to a talk by George Shultz, the previous secretary. So halfway, I set it up with the organizer. Halfway through his talk was the exact moment we were taking the picture. So the organizer stand up and said, "Mr. Secretary, we have to interrupt you for something which happened only once in a lifetime." So I stood up and told everybody to look east and wave. And then after I explained to them why we're telling them to do that. So even George Shultz said, "Wow, that's a great idea. Can I get a picture of this thing?" So there are lots of people in that dot actually waving, and that's a blow up to show you us and the moon next year. So now I'm going to show you, think all what we do is Mars, so I'm going to show you what we did in the last year.
Astronomers report the discovery of an Earth-like planet about 600 light years away from here. It is called Kepler 22b, and they believe it has a temperate climate in the 70s all the time.
Wide Field Infrared Survey Explorer. The images are breathtaking, proving once again Earth is a teeny tiny part of the universe when compared to everything else that's out there.
Scientists using NASA's Spitzer Space Telescope have discovered what appears to be an alien planet just 2/3 the size of the Earth. A heat-blasted world perhaps covered in molten lava.
And Pegasus is away, standing by for ignition. And we have stage 1 ignition. Ignition of the Pegasus rocket with new star for an understanding of the ultimate destinies of our stars and galaxies.
And we have big news from out of this world tonight, specifically from one of Saturn's moons. A spacecraft operated by NASA's Jet Propulsion Lab has just confirmed that the basic building blocks for life exist.
Tonight, there is new information that reveals just how fast the world's ice sheets are melting.
Polar ice sheets in Greenland are melting at 5 times the pace of just a few years ago.
NASA's Mars Reconnaissance Orbiter spacecraft captured a photo of a gigantic dust devil racing across the surface of Mars.
From that image, we can reconstruct what this would look like if we were able to get an oblique view, as if we were in a helicopter flying around the dust devil.
We knew there were black holes, but so many? WISE found millions. Even in this tiny patch of sky, there are dozens. The infrared cameras captured the extreme variety, too. Supermassive black holes known as quasars.
This is the first time a spacecraft has orbited an object in the main asteroid belt, and I want to congratulate everybody on the team on an outstanding job. This is a really unique accomplishment. Congratulations, everybody.
Thanks to ebb and flow, we now know a lot more about our celestial little brother, including that its crust is much thinner than scientists assumed.
This video was made by Ebb as it flew above the surface of the moon that we don't see from Earth.
Ebb and flow will be given one final instruction: to aim themselves directly toward the lunar surface and fire their thrusters.
The American Space Agency says it will send a new vehicle based on its Curiosity robot, which landed on Mars in August and has sent back detailed images of the landscape there.
Voyager 1 is now 120 times as far from the Sun as the Earth is. That means it's 11 billion miles out. We're very near the edge of the bubble the Sun creates around itself, called the heliosphere. We're getting very close to the boundary.
We should have parachute deploy around Mach 1.7. The parachute is deployed.
So you are going to see this a second time.
Feat shield has separated. We're on the ground. Standing by for back shell separation. We are in powered flight. We're at an altitude of 1 kilometer descending. Standing by for sky crane. Sky crane is started. Touchdown confirmed. We're safe on Mars. Time to see where our curiosity will take us.
So that's what we're doing at your behalf. So let me finish with one last slide, which for me is probably an iconic picture. On the left-hand side, that's the footprint of Neil Armstrong, on the moon. And I remember very clearly exactly where I was, who I was with. I was still a student at Caltech, sitting in a student house with a bunch of friends of mine. And for me, it was amazing. It was something I was saying, wow, we can even land on the moon and put our footprints on the moon. And that kind of inspired me, in a sense. So the one on the right is hopefully what inspires the young people sitting here. That's a footprint of the rover on Mars. So just to think that the humanity, we can go to another planet and we actually can put our footprint, on another planet. So hopefully that will inspire, the next generation and basically allow them to do a path that none of us have done or none of us have dreamt of. So again, thank you very much, and hope. So I think the way I understand it is that the questions will show up here if you are good at tweeting. But if you don't know how to tweet, I'll be glad for you to, the old-fashioned way. You can raise your hand after and do that. So first question is, what were some of your biggest engineering challenges when building the Mars rover? Now, clearly there was a lot of challenges, in doing that. But I'll tell you what I was mostly nervous about, sitting in the mission operation room. I was really nervous about the parachute. Now, everybody immediately think about that sky crane. But we were able to test the sky crane. So we had helicopters, we dangled things from under the helicopter. We put, like the radar systems that we use, we put it on an F-16, flew to a very high altitude and had the plane dive, coming down at the speed, almost like the speed we are coming at. But the parachute, we packed it 3 years earlier. And there is no way you can test the actual parachute. You test an identical parachute, but the actual parachute, you cannot test because once you deploy it, we won't repack it and do that. So that's what I was mostly nervous about. And this was a parachute which was opened at supersonic speed, and it was the largest parachute ever built. So when we saw the signals, the parachute opened and we started seeing the spacecraft slowing down, I said, we're 90% there. So that's the one which I considered the biggest challenge. A lot of other things were challenging also. See, can we get there another one? Okay, does JPL license its technology? If so, have you had any inquiries? Yes, the answer is the following. There is a law which said, because we are part of Caltech, of a private university, even that we are a NASA center, but all the employees at JPL are part of Caltech. So it's what's called FFRDC, for federally funded research lab. So I'm part of Caltech, I'm a faculty at Caltech. So all the licensing right goes to the university, like any university in the country. There are inventions which occur at the university. So we do have an active office, at JPL and at Caltech to license and inform industry about all the technology we have. So let me give you a couple of examples. I'm sure you all have a cell phone. You all have a little camera in that cell phone. The focal plane in that camera, which actually takes a picture, that was invented at JPL about 15 years ago. We have the license on it, and every time you buy a phone, we get a few cents, from that thing. So that adds to a lot of money, and where it goes to support students at Caltech for their education. So it's a double benefit that you get from it. It's an investment in the next generation doing that. So that's just one example. The other one is the arm that we have on the rover. A lot of that technology is licensed to companies which actually do remote surgery or developing the remote surgery capability with the arm that they a surgeon actually uses remotely to actually do surgery. It's exactly the same technology that we have, and we have licensing on it. So there is a licensing office at Caltech which also cover JPL if you are interested to know more about what we do. How are things progressing on the James Webb Space Telescope? James Webb Telescope is the next generation telescope, which is after Hubble. Now, Hubble is about 1.5 meter, size, and got all those great pictures like what I showed you at the beginning, of the galaxy. James Webb is about an order of magnitude more capable in sensitivity and resolution. So it will allow us to actually see all the way back to almost 300,000 years after the Big Bang. So that's seeing almost as back before galaxies actually were formed. Now, it was challenging. In full disclosure, it's not at JPL. It's done by the Goddard Space Center, but it's being built here at Northrop Grumman. There was a lot of challenges because it's a very, very complicated telescope. It has to be cooled to a very low temperature. You have a tennis field size shield, which have to protect it from the sunlight to do that. But all indication, but we are involved because we are building some of the instrument. All indication is that they are on track for a launch in 2018. So keep your fingers crossed. Hopefully all the engineering challenges will be surmounted, and then you will get a much more detailed image than what you saw earlier, come 2018. When will women land on Mars? Now it said, when will men and women land on Mars? Whoever wrote it, you should reverse. I have 2 daughters only, so I put the importance on the women. Let's put it this way. Sending a human to Mars is very challenging, but it is within our scope of capability in the next couple of decades. Now, why is it challenging? First, going to the moon takes 3 days. So when we did the Apollo program, it was 3 days going there. You can spend a few days and you can come back with it, and that's all what you need. Going to Mars is 9 months, and you have to spend a few months there, and you have to come back is another 9 months, so you're talking about 2 years. Just imagine at your home how much food you need, how much water, how much trash you generate, how much medicine you need, and so on for 2 years. And all of that has to be carried, with us, So it's a challenge. You would need a very large spacecraft, and it's a challenge. And I think it could be done, in the next 20, 30 years. But so you can land, and then you can have rockets bring you back. So some of the examples you can do is, and that's some of the research we are doing, is after you land, we know there is water on Mars. It's all in ice. It's frozen under the surface. So you can extract the ice and the water. You can drink it. And then the other thing, you can break it into hydrogen and oxygen and use that as a fuel. Many of our rockets actually use hydrogen, and oxygen fuel, to fire the rocket to bring. So there is conceptually, there is a way of doing it. The practical is how do you do that and do the engineering, so on. The other factor is radiation. So once you get beyond Earth's shield, which is the atmosphere, you are exposed to the sun, UV radiation and sun radiation. So that could have impact, and there are medical doctors here that have a lot of impact, how much radiation you can absorb your body. And the final thing is psychological. Going to the moon, if something goes wrong, it takes you 3 days to come back, and the Earth is still sitting in there. Going to Mars, the Earth starts disappearing, and it's only like a little dot. And once you fire that rocket, you're not coming back for 2 years, no matter what happens. So there are still a number of challenges to do that. But I think it's not inconceivable that within the next, I would say, 20, 25 years, we actually can go and land on Mars. Now, some of you probably hearing about Dennis Tito, who some of you might know him, is talking about sending a human in 2018. That's not completely crazy, because turn out every 18 years, the planets are aligned in such a way that you can go relatively fast, to them. So 2018 is a very good year. 2036 is the next very good year. And what he's thinking about is to send a spacecraft to go to Mars, just loop around Mars and come straight back, not to even land. So that's still 18 months. It's going and coming back. But it's one of the most efficient way, energy-wise, to do it. Now, will he be successful? Matter of fact, we are working with him about some of the engineering challenge. It will be challenging, to do it, but it's not crazy, to do that. So it's one of these things that, you need people who are kind of out-of-the-box thinkers who can do these kind of things. So yeah, within many people here lifetime, we probably will be landing people on Mars. What system on Curiosity is expected to fail first? Probably my heart will fail first after I watch too many of these movies. First, the power is not an issue because we have a nuclear system that will take at least 8 years. So probably the most likely is some of the gears. You know, it's like your car. After a while, after 5, 6, 7, 8, 9, 10 years, some of the gears can go down. Now, to give you a reference, Spirit and Opportunity, which we launched 10 years ago, come January, they were supposed to work for 90 days. One of them failed 8 years later. The other one is still working 10 years later. So we tend to be pretty conservative in our design because these are unique opportunities. You don't send rovers to Mars every other day. So I would expect, unless we do a human mistake, that we send the wrong command or get it in a ditch or something like that, probably it will go for at least a decade, working that. But most likely the gears will be the first one, to suffer. How will government budget cuts impact JPL over the next decade? I mean, no question we depend fully on the government, for our funding. Or, matter of fact, I would say on you, not the government. You are the taxpayers. You are funding the government. And clearly there are budget challenges and budget issues. And there will be some impact. But what I can say is, we landed on August 5th. The conversation in Washington on August 6th was very different than August 4th. It really created an amazing environment of people being uplifted in Congress and the administration saying, wow, we can do these great things that our country can do. I mean, before it was all depressing, what we cannot do, what, all the problems we have. So literally within a month after the landing, we had 2 Mars missions which were approved. One which will be in 2016, will be landing not a rover, but a fixed lander, which will have a seismometer on it, which was provided by the French, which will be provided by the French. And we are trying to see if there are the equivalent of earthquakes, on Mars. Now you say, why is that important? That's how we learn about the internal structure of Mars. The reason we know there is a core in the center of our planet and how it is layered is by looking at the earthquake signal and how they propagate. So we'll be doing the same thing, for Mars to see what's the internal structure, how big is the core, because some theory is the reason the activity on Mars stopped and was extinguished is that the core of Mars is much smaller than Earth. And therefore, the heat in it dissipated much faster. That means after 1 billion years, Mars became a very cold place. So that's one. And the other one, which will be in 2020, it will be a rover similar to what we landed here, except it will have a different purpose. What we'll be doing, we'll be driving for a couple of years, look at the most interesting samples, collect them, put them in a canister, put that canister in one location, so later we can go land, grab that canister, and bring it back to Earth. And then we can analyze it in much more detail here on Earth. Now, having said that, still there is a pressure, so if you're connected to a congressman or a senator, please tell him that we can use more money, and you saw all the benefit for Earth application and so on, and to give people a perspective. Because people say, wow, this is all expensive. How much does it cost? That mission, the rover that we landed, to give you a perspective, that cost less than a movie ticket per American citizen. So that costs $6 per American citizen. So you can be a judge. Is it better to go and see a movie for $6, or is it better to do this kind of thing, for an American? So that gives you a perspective, of how expensive or not expensive these things are. What do you think about Elon Musk's SpaceX? I think it's a great company. I think Elon Musk is a very imaginative person, and these are the kind of entrepreneurs that our country strive on. I mean, the way I put it is our country is so economically strong for 2 reasons. We have a lot of innovators, which come with new ideas, and we have a lot of entrepreneurs, or our system allow entrepreneurship of people to fail and then try again and then try again until they succeed. That's what makes our country so powerful economically, is that combination of innovation and entrepreneurship. And I would say Elon Musk is one of the most entrepreneurial people. He's not doing anything new technologically. It's all technology which have been developed by the government, by NASA. But his entrepreneurship is to do it in a more cost-effective way. It takes that technology that you all invested in into, and basically develop a new capability and a new company. So we wish him all the luck to actually be successful and hopefully to sell his rocket at much lower cost so we can do more mission like what we are doing. What groundbreaking space exploration mission are planned for the next 10 years? So let me describe a couple of them. One is the 2 Mars mission that I just described to you, and then probably by next decade, we'll be able to go land and bring those samples back. Another mission which is very exciting in my mind is a mission to go to Europa. Europa is a satellite, of Jupiter. It's about a little bit bigger than our moon, but we know it's all made of ice, because we have done from Galileo and Voyager. And we do see organic material on the surface. And we also see that that ice is kind of moving, over many years, similar to what you see in the North Pole. So it's like that's ice floating. So we think there is an ocean just below the surface. And the fact that the ice is made of water and the ocean is fluid because it's floating on it, the next question is, could life exist in that ocean? So what we want to do is to go put an orbiter around Europa, sound that ice, find how thick it is, and in an area where it's relatively thin, sometime in the future, we might be able to put a lander, melt our way, and get down to that ocean. In a similar way, if you read scientific magazine, people have melted their way through Antarctica, some of the ice, and got to some of the lakes which are under the ice, and they are starting to analyze those samples. Or if some of you, I think there is a movie called Europa Report or something just coming out. I'm not sure how, I watched it. It's an okay movie. But at least it shows some of the things about why Europe is exciting. And the last one, which is particularly exciting, is looking at neighboring planets, neighboring stars, and see the planets which are around them. 10 years ago, we had no proof that there are planets other than our solar system. Today, on the latest count, we think there is at least 2,500 planets that we actually have detected by using indirect techniques. What that means is we look at the star, and you measure how bright it is, and if you see a dip in that light, that means something came in front of it. And if that dip repeats, that means it's something which is in orbit around it. How big is the dip will tell you how big is the planet which is blocking that light from in front of it. So indirectly, we have determined there are thousands of planets, so they exist common. Next big step, what we want to do is to block the light of the star so we can take picture of the planet. And that requires very large telescopes, which are very, very accurate. So there is a lot of technology which have to go in building those telescopes. And that's something we can do in the next probably decade. So if the Milken Institute invites me 10 years from now, I might show you a picture of our neighboring few hundred stars and show you family portraits, of the planets which are around them. Could you comment on the 100-year Starship project originated by DARPA? What is your prognosis for 100 years downstream? And is JPL involved all with this 100-year activity? I'm not exactly familiar with the program that people mentioning here, but we have been looking in the past of sending a spacecraft to the neighboring star, to go beyond our solar system. Voyager is the first one. Now, we didn't plan it specifically, but it survived. The challenge is that the nearest star to us, with today's technology, will take you 70,000 years to get there. So I don't think we'll have the patience to do that. So the key thing is, can we develop more advanced technology, particularly for propulsion, so we can move faster, on it, which will allow us to get there in a lifetime. Again, it's not crazy. It's not against the laws of physics, but we need to get things which go to move almost at the tenth of the speed of light. And we don't know how to do that yet now. But we didn't know how to land on Mars 50 years ago either. We didn't know how to fly on an airplane 150 years ago. We didn't have cars 200 years ago. So within the next 50 years, it's not unreasonable that we'll be able to send starships to the neighboring. Now, people here need to tell me if I need to stop. I'm getting here on a roll, okay? What happened to the sky crane after it dropped off the rover? Actually, it went and crashed, on Mars. I didn't have the picture here. We actually do have a photograph which shows the rover where it landed, and the sky crane, the thing which then separated, actually flew and crashed, about a mile, away from it. And then next to it is a heat shield, and a little bit farther away is the parachute. And for the fun of it, we usually take picture and see how the parachute is kind of blowing in the wind on Mars, and it actually does move, a little bit. Is that it? Oh, sorry. Do you have any theories on how to answer the Fermi paradox? This must be one of the young people here who asked that. I really don't know an answer to that one. Sorry. I'm only the director of JPL. The real work is done by the staff. So I don't have an answer to that. I don't know. Why are the rotation of Mars and Earth so similar 24-hour, considering their different physical characteristic, solar orbit size? We don't know. I mean, that is really a very intriguing thing, because different planets rotate at different speeds. Earth is 24 hours. Mars is 24 hours and 20 minutes. Venus turns the other way every 180 days. So this is one of the dilemmas that we have in figuring out why different planets rotate, at different speeds. And by looking at neighboring solar system, at other stars with planets around them, that will shed light on how our solar system formed. Because we think that our solar system is typical, that you have rocky planet next to the star and big planet farther away. We're finding that planetary systems are all over the place. We're seeing some of them which are rocky planet, but they are huge, and small gaseous planet outside, or big planets are close to the star, and small planets are outside of it. So this is opening a whole new field of understanding how do planets actually form, and how did our solar system form. And that might shed some light, as we model these things about why they rotate differently. How did you feel about the risk of setting up watching location for the public to see the landing? Were you worried about a mishap being showcased to big crowd? Yes, I was worried very much. But, no question what we do is risky. No question when you do exploration, it's risky. Almost every time we do something at JPL, we're taking a risk. But that's what explorers are about. When you explore something new, you're always taking a risk to do that, because you don't know how to do it. Otherwise, we would have done it. If it was easy, we would have done it, before. So the key thing, what we have done, because we knew we are going to be watched by lots of people, is to explain to the public the difficulty and the challenge of what we are doing. So we had this video called The 7 Minutes of Terror. Some of you might have seen it, which we put on the web before, and you saw only a segment of it in here. So we put it on the web to really tell people this is a tough thing to do, and it's very challenging, but it's worthwhile to do it. So I think with that thing, there was a lot of sympathy in the public of saying, wow, these guys are really pushing the limit. They are doing something almost impossible. We want to wish them success, but if they fail, at least we'll understand it, why they're doing it. So by being open with the public and explain the challenges and the difficulty and the benefit, I think it created two things. One, understanding, but number two, everybody was there cheering for us, hoping that we'll be successful in doing what we did. And the fact that it was successful helped. Now, a little secret, at the landing there, I had 2 speeches in my pocket, one if we are successful and one if we are not. As soon as it landed, I took the one that were not, I tore it and threw it away. I didn't even keep it. I didn't want even to see it. What about cross-galaxy travel via wormholes? Again, this must be, did you put that question? Today these are science fiction. But as I said earlier, 100 years ago, going to other planets was science fiction also. So who knows? One of the key things which is important in science is to keep an open mind, about things, because you can never tell what discoveries will happen, and somebody will make a major breakthrough, which could happen. We all now think that a few years ago, we always thought that we knew all the mass in the universe, that we think based on all what we saw. We found out that we really don't. We knew the mass in the universe that you can see is only a small percentage of what actually exists. And that's what you hear about dark energy and dark matter. And the reason we know they exist is we see that the galaxy rotate at speed completely outside the models that if we knew the mass of the galaxy. Because we can model, if we can determine what we see, we can model how fast the galaxy should spin. Well, it's spinning at a different rate, at a higher rate. We can determine how fast the universe expands. We're finding that it's expanding faster than we thought. So clearly there is something that we don't know that actually is forcing that to happen. So that's what's called dark energy and dark matter. And now we're thinking of ideas and mission to actually detect, their presence. So we can determine how much dark energy, and we might find completely new discoveries that we haven't thought about that. So that could be possible on doing that. So Hollywood is not that crazy when they do these things. How could a young person best prepare to increase their chance of an opportunity to work at JPL? Well, I have an application form. If you want, I can. No, this is a very important question because we do feel that we have responsibility to the country. I mean, we are in what I consider we are a national asset. JPL exists because you all invested in JPL. This rover is not my rover. This is your rover. You paid for it. You cheered for us. Some way, one way or another, you were involved in it. So we go out of our way of engaging young people in knowing about JPL, space, so on. So if any of you want to bring student or your kids who are at school, you want to come for a tour of JPL, we have almost 25,000 students visit JPL every year. So we organize tour for them. We work with their teachers, to have them come and visit. We have an open house at JPL. We do once a year. We don't have the date for the next one. We were planning it last May, but we had to delay it. And then the last thing, in the summer, this summer, if you come to JPL, it looks like a campus. We have 750 students working at JPL just for the summer. Starting from high school, they have to be older than 16, in college also. So we are and part of that reason, other than, we are excited about doing that, is we are part of Caltech, which is an educational institution. So part of our job is to educate the next generation. And for the older generation, so you don't feel left out, we'll be glad to organize tour for you if you want, to come to JPL. So we always like to show off what we have. Dark energy or modified Newtonian physics. Now, it really passed way over my head. I really don't know how to answer that question. Anything? Okay, I think we're out of question here. There's a lady back there. Oh, sorry, there is one more, then I'll get to you. We noticed that Curiosity look a lot like Wall-E. Did the movie studio get in advance? No, in actuality, it's partially correct, your statement here. It looks a lot like Spirit and Opportunity. Wall-E looks a lot like, and yes, we did work, with Disney about that. We work a lot with Disney Imagineering. They are very close to us, about 15 minutes. And it's amazing that their activity is very similar to our activity. I mean, they work on projects similar to what we do. They are doing things which are really amazing. They have to do them safe because they have the public which is involved in them. In our case, we cannot bring them back to repair them. So we have a lot of the same mindset of how we do things. So we exchange. But in fact, one of the vice presidents at Disney is at JPL tomorrow giving a lecture of how actually they design, their activity. Did you see any good ideas in the Da Vinci book that we will see on JPL next spacecraft design? Maybe let me tell you another one. I didn't bring the video. I mean, I didn't show it in the view graph. In Spirit and Opportunity, when we landed, we inflated those airbags. As I was looking through the book, he had exactly the same thing because he was trying to describe if there is a human which flies and the machine fails and they fall down, how do you protect them? And he had this picture with a bunch of airbags, around it. So who knows? Do you believe aliens have visited Earth? No. Now, to be clear, I think life exists in the universe. There is no doubt in my mind that there is life similar or different which exists across the universe. The question, did the life visit us? I think it's unlikely. I mean, maybe I shouldn't say an absolute no. In science, you never say absolute no. And the reason is what I said earlier. The nearest star to us takes, at our technology, takes 70,000 years to get to it. At the speed of light, it takes 4 years for lights to get from the nearest star to us. So aliens have to be extremely advanced, in their technology to actually, that could be possible, So my no is a soft no, not a, I want to make sure I take the question of the lady back there.
My question was that you talked a lot about what sort of projects you have going forward. Is there a particular passion project of yours, what you have at, the technology and things you've seen at JPL that either you wish you could work really and spend a lot of time on, or that you wish that was that could or would happen?
You mean For technology, you're...
Technology, like in terms of, versus you were talking about, going and slinging around Mars or whatever. Is there something passionate that you wish that
Me,
you were spending time on?
Well, the people who know me here, like the gentleman, they know I'm passionate about all kinds of things. No, I think in the technology area, for this kind of thing that we do, you really need technology across the board. There is no single one technology which enables something. If I have to pick one, it's really like the propulsion technology to go faster, to get there, because that will enable us to access, to give you an example, to get to Saturn, because it was 7 years just to get there. So by the time you build the spacecraft, you get Congress to approve it, you build it, you get it to Saturn, that's like 25 years, to do that. So if I have to pick one technology which could make a huge difference, I think it's a propulsion technology to do that. Having said that, that's not enough. I mean, you really need technology across the board. I mean, today, all the software development which is being done, the miniaturization that have been done, enabled us to do, this rover that you have here, or let me backtrack a little bit. The kind of technological capability and memory and electronics we have here would have been unthinkable, a decade ago. So it allowed us to do amazing things we would have never been able to do with 10 years ago electronics or technology. The materials that we have to develop, to survive that environment on Mars. So we need advanced material. So it's really literally across the board technologies that you need that makes these things happen. One more? Okay, I'll take one more as a gentleman. And then I can hang around a little bit here if you want to come to the front and ask. Oh, I let the lady here decide. Sorry, I can take it after. Yeah, go ahead. Was it you? No, the gentleman.
I'm sorry, I can't see you.
Okay, I'll take 2 questions.
Okay, well, thank you very much. I'm just kind of curious. Can you tell me approximately how fast are we moving as we are here in this room right now in space?
Oh, I wish I remember that. You're moving at many thousand kilometers per hour. I mean, Earth's going around the sun.
Yes, considering all factors, with the rotation and everything, how fast do you think?
You are moving at many thousand kilometers, per hour. You don't feel it, but you are moving at that speed.
Thank you.
And I think there was one last question.
Just very briefly, you have a very slight accent. I was wondering where your early education was and when you came to America.
Should I tell him? Yes. Oh. No, I was born in Lebanon, in a little village, from a very average family. My parents didn't even have a high school degree, but they felt that education was very important, for their kids, for me and my brother and sister. So that was the highest priority for them. So they spent all their money educating us, making sure we go to good schools. Then I did my undergraduate in France, so you might see a touch of French. In there I was in boarding schools, in French schools in Lebanon. Then I went to France. And then for a story that I could tell you in private, I ended coming to Caltech, for my PhD. I had the choice of MIT, Stanford, Caltech. I looked at the map. I saw Caltech next to Hollywood. I said, wow, I can see movie stars. That will be a great place. I mean, literally, that was, when you are that age, that's what I was very much in movies. Errol Flynn was my hero, So I thought I'll come and I'll see him next door and so on. So I decided on Caltech, never left. And I haven't met any movie stars yet. Thank you very much.
Dr. Elachi, thank you for taking us to new heights. And it will be definitely less than 10 years before we have you back. Thank you so much. And we promise we'll introduce you to a movie star if you'd like.